Harold Baranger is one of the architects of the field, formerly known as mesoscopic physics. I think it's called mesoscale and nanoscale physics now. He's best known for his pioneering work demonstrating quantum chaos in small semiconductor devices in the regime of ballistic quantum transport. But much of his recent work has been on waveguide QED and dissipation and correlation effects in quantum dots and quantum wires. He's going to tell us about something a bit different today. And from his website, I see that he also works on quantum machine learning applied to noisy intermediate scale devices. So clearly I can't do justice to all the exciting work in which he's engaged in an introduction of finite length. But fortunately I don't have to, many of us know him well. Harold did his doctoral work at Cornell and was for a long time a member of the technical staff at the legendary Bell Labs. For the past 2 decades, he's been a professor of physics at Duke University, where he's also served as department chair. I should mention that Harold is an old friend to many of us and to the department, so we are delighted to have you here, even if it's only virtual. Welcome, Harold. The floor is yours.
Oh, thank you very much, Harsh, and thank you for the kind introduction. It's a pleasure to be back at CASE in some sense. Yeah. Okay, so I want to tell you today about a recent project about an interface, creating an interface between a quantum Hall state and superconductivity. And in particular about these things called chiral Andreev edge states and the interference between them. This is work that I've done in collaboration with a student here at Duke, Alexei Bondarev. And you'll see that it's heavily experimentally motivated. And I'll be showing data from the team of Gleb Finkelstein here at Duke. So the idea is to just consider an interface between a superconductor, an S-wave standard superconductor, and a quantum Hall state, and ask what kind of modes exist there. And in particular, there's a certain resistance, which will be, I'll define and be talking about, which goes both positive and negative. And it's surprising in some sense that it goes negative, and that's been observed. This is the data that from the Finkelstein group. Let's see, hang on a second. Now there we go. So what's the motivation? Well, the motivation is that one of the motivations is there's been a lot of interest in interfaces between distinct quantum states, right? I mean, we start out in condensed matter physics, of course, by concentrating on describing the state, the quantum state that we're interested in. But over the last couple of decades, there's just been an enormous amount of interest in what happens when you put two sort of qualitatively different distinct states together. And I just, chose some examples on this slide, which I'm not going to particularly talk about, but just kind of to jog your memory and point out that you've heard about this before. So one of the first and one of my favorites is that there's these two insulators that you can stick together, strontium titanate and lanthanum aluminum oxide. And at the interface, you get a two-dimensional electron gas, which actually becomes superconducting under certain circumstances. So the strontium titanate is one of the favorite material systems that people are using for these interfaces. And there's a review and some examples that have been discussed recently. Now, of course, in the last 10 or 15 years, one big impetus to this whole topic has been topological physics, and in particular the discovery of topological insulators. And what happens when you have an interface between a topological insulator, here's just a simple one, a quantum spin Hall system, and a conventional insulator. And we know that there's some topologically protected states at the interface. So this is a two-dimensional example, and then there's also three-dimensional examples. This is a calculation of the local density of states in a 3D topological insulator showing this edge state, the surface state here, and which was then seen experimentally using ARPAS. Okay, that's not. So I'm not going to be talking about those materials, but there, and what I'll be talking about, there is perhaps a connection with Majoranas. So let me just remind you with the Majoranas, Majorana fermions are a way of rewriting our normal Dirac fermion operators in this way. And they turn up, I mean, you can always write your fermions as Majoranas, but they turn out to be useful and interesting in a couple of different contexts. One is certainly frustrated spin systems. That's where they were originally developed. The two-channel Kondo effect is one of the oldest, about 30 years old. And then this Kitaev model in which you have a spin chain and you pair the Majoranas instead of in the natural way in an unnatural way, so that you've unpaired Majoranas at the end, attracted a lot of attention. Now, I'm going to be talking about quantum Hall plus superconductivity as an alternative direction. And there's a couple of works. Here's a few along these lines. So for instance, there's been work on what happens when you put a superconducting island in a nu equals 1 quantum Hall state, and you get a Majorana going around the edge like that. And then there's increasingly more complicated cases if you go to fractional quantum Hall effect, where people have talked about these things called parafermions. And also there's been work, for instance, on again, fractional quantum Hall effect systems in which have an interface between them involving superconductivity, producing sort of interesting fractional charge systems. Okay, but this is for the moment beyond what's experimentally possible, and I want to talk about sort of getting started, right? I mean, this talk is going to be kind of like a first step in these directions. I'm not going to be able to show you how to make any of these more interesting states. But let me start out. I'm not quite sure what the background of the audience is here, so I thought I would start out with just a few quick words about the quantum Hall effect and also Andrei of Reflection. So let's start with the quantum Hall effect. So in a quantum Hall effect, you have you have cross fields, a magnetic field and an electric field. And if I'm looking at the bulk, the electrons just have their cyclotron motion like so. And if I'm considering the edge of the system, then they have this skipping orbits along the edge like so. And you can see that the ones on this side go in the up direction and the ones on that side go in the down direction. Now, when you go to the quantum level, right, these orbits are quantized, and therefore you get in the bulk, you get Landau levels, so a spectrum which has these sort of discrete states. But on the edge, because of the confining potential, right, that energy changes and it comes up, it rises up to the Fermi surface, so that you have these edge states where the Fermi energy crosses those energies. Okay, so you have these edge states along the edge of the system, and the motion is in a fixed direction, which one calls then chiral edge states. Okay, feel free to come off mute and ask me any questions as I go along. Now, what about superconductivity? So I want to talk about Andrei of Reflection, which is what happens at an interface between a normal system and a superconductor system. So here's the classic context where I have two superconductors and an insulator in between, and I'm talking about a Cooper pair from one superconductor tunneling into across the insulator, which is a normal region after all, into the other superconductor, right? So this is the classic Josephson effect that was discovered and then observed by Anderson and Rao. Well, Rao's the experimentalist, right? Observed by Rao subsequently. Now, right, we want to view this in terms of what's called Andrei of Reflection. So if I want to consider a situation in which instead of having an insulator there, I have a normal metal, right? So this is a normal metal with a Fermi surface and, you know, electrons at the Fermi surface. And so consider an electron which is coming along like so, and it hits the superconductor. What happens? Well, of course, one possibility is that it just scatters and is reflected, you know, as an electron. But the other possibility is it cannot go individually into the superconductor because of the superconducting gap. I'm imagining that the energy of this electron is below the superconducting gap. So there's no single particle states that are available. But there is the condensate, of course. So it is possible for this electron to make a transition into the condensate by grabbing another electron and making it come with him, making this Cooper pair. So one way to view that is that, you know, I've grabbed that other electron, and so that leaves a hole behind in the normal metal, right? Which is this black dot here. And that hole goes in the opposite direction. Why is that? That's because in the superconductor, the momentum of the two electrons are opposite, right? It's K and minus K. So that when this electron goes in with momentum K, the momentum it grabs to come with it is at minus K. And so the hole is at minus K and is going in the opposite direction. So this Andrei of reflection, then the electron comes in and the hole goes out. And you can develop a whole understanding of the proximity effect through this Andreev perspective. And there was a nice summary sort of review article done by Klapvik in 2004. Now, one's often interested in the case where there's two superconductors like here. So then what do? Well, the hole comes back here and the hole will reflect itself as an electron. Right? So there's a trajectory, there's a closed trajectory sort of reflecting between these two surfaces. And when you go to quantum mechanics, that should be quantized, right? So you get a bound state of the system, and the current will just be proportional to the phase sensitivity of that bound state. Okay, so before going on, I just want to mention that this may seem kind of strange to you, right? Because superconductivity, after all, is a pairing of time reverse states, right? I've in my simple example that's kind of come up in the pairing between this electron and the hole. Well, the fact that the two electrons that go in have opposite momentum. But it's actually much more general, right? If I consider a disordered system, I can pair these disordered wave functions which don't have any definite momentum, and still I pair time reverse states in order to get superconductivity. But on the other hand, we're used to thinking about the quantum Hall effect as something that happens for large magnetic field, right? One of the conditions for the quantum Hall effect is that omega c tau, the cyclotron radius times the scattering time, should be much bigger than 1. And typically that means that omega c, the cyclotron frequency, has to be large, or in other words, that the magnetic field has to be large. And magnetic fields, of course, break time reversal symmetry. So it seems like there's a sort of fundamental contradiction between trying to put these two states next to each other. So how do you do that? How does it happen? So here's the structure that the experimentalists use. So, so the key is to use graphene. That's going to be my normal metal in this system. The normal metal is going to be graphene. And the thing about graphene is that it's so clean that it actually has a very nice Hall effect by 1 Tesla. Okay. And on the other hand, it's not hard to find superconductors that have an HC2, a maximum field that they can sustain of, considerably more than 1 Tesla. Okay, it might not be easy to find one of that type, which you can use and make contact to graphene and all the experimental things and so on. But they were able to do it. And the superconductor that they use is this alloy of molybdenum and rhenium, which has an HC2 of about 10 Tesla. And the graphene that they use is encapsulated between boron nitride. Now, boron nitride is an insulator, also with a honeycomb structure, and it's very closely lattice matched, so that if you sandwich your graphene between it, it's a very sort of clean and nice way of having a pure graphene conducting sheet. And that way tau is very large, which helps in seeing the quantum Hall effect. What else do I have here? And so you can see the quantum Hall effect. This is the conductance in color scale, going from in units of E²/h, y, as a function of magnetic field. And this axis is the gate voltage. So what I mean by that is, in this sandwich structure, you can see silicon dioxide is an insulator, of course, but the silicon here, the silicon is doped. So that actually, it can conduct, and you can use the potential on that silicon layer to change the density in the graphene. That's what I mean by the gate voltage V sub G. And so you see it has you definitely see your nice plateaus, your Landau fan. It looks like it has a pretty good, a very nice quantum Hall effect. So how are we going to think about these interface modes? Okay, because I mean, I said that at the edge of the quantum Hall, so if I make a interface between the graphene and just vacuum, just the edge of the graphene sheet, in the quantum Hall regime, there'll be an edge state going along there. But now I'm going to have a superconductor which has a gap. So in some sense, there should be an edge like that. But when the electron comes along, right, it's going to Andreev reflect from the interface rather than just a regular reflection. So I'll have this alternation between electron and hole, like so. So I'll have an edge state, yes, but there'll be a mixing between the electron hole. It will be a hybridized electron hole edge state. So this is the semi-classical picture in terms of these skipping orbits. And when you go to the quantum regime, for instance, this is the case if I just had one Landau level in the bulk below the chemical potential, then at a vacuum interface, I would have one edge state. And here I'll have an electron edge state and a hole edge state, right? And so that's what's shown here. And I first learned about this this kind of thing from this paper in 2000.
So Harold, this might just be a matter of convention or something, but should the arrows on the hole state run the other way? Because
no. So thank you for pointing that out, because they should not run the other way. So the point is that in the magnetic field, the holes are bent in the same direction as the electrons. So here in the semi-classical limit, I mean, right here at the reflection, yes, the hole is going opposite. But when you figure out now which way the magnetic field is going to bend the hole, it's going to bend it in that direction.
Okay, yeah.
So very different from in the, actually, I really thank you because it's a point I meant to make. Very different from in the regular normal metal where the hole is really going in the opposite direction. Here, it's flowing in the same direction along the interface, okay? And that's how they get, that's how they're going to be able to be mixed by the superconductor.
Yeah.
Mm-hmm.
So I guess one way to think about it is you need to think about what that electron state, which has been emptied out, would have done. And then the hole, of course, will do the same thing.
The hole does the same thing, exactly. That's exactly how you think about it, yeah. Mm-hmm.
Okay.
Okay, so just a slide on how we're going to approach this. I'm going to show you some numerical results from a sort of tight binding approach, and then also I want to just show you how you would think about this sort of in the continuum model. So in the tight binding, here's my tight binding Hamiltonian. Now, the first thing you notice is that there's these things tau, which you perhaps didn't expect. And the thing is, this is the tight binding Hamiltonian for both the electrons and the holes, right? I'm going to do, well, I'm going to sort of do Bogoliubov again. I have to consider a Hamiltonian in that sense. I have to consider what's happening to both the electrons and the holes. And the way you do that is you double the number of degrees of freedom. So that's so-called Nambu doubling. And so these taus are Pauli indices in that electron hole space, right? So you can see this is the on-site term, the on-site energy term, which we've just called the chemical potential. And that makes sense because it's going to be, you know, put the electrons one way and the holes in the opposite direction, so tau z. And here's the superconducting gap, the order parameter, and it's multiplied by tau x because it connects the electrons and the holes, okay? And then I have nearest neighbor hopping, and in the nearest neighbor hopping, because I have a magnetic field, I have to have a phase factor. This is the so-called Peierls substitution for the phase that the electron acquires when it hops in a magnetic field. And there's a tau z, you know, because the electron and the hole have opposite charge. So that's my tight binding Hamiltonian. And if I look now in the low energy space, so remember in graphene, we're going to be interested in what happens at the Dirac point. So will be the experimentalists typically keep the chemical potential pretty close to the Dirac point, though not exactly at the Dirac point, because there's problems with sample inhomogeneity if you go right to the Dirac point, but nearby. And so if you zoom in on that point and ask what's the effective Hamiltonian, then what you'll find is the following. So it's going to be off diagonal, right? So now I have to introduce sublattice space, right? Which is going to be these Pauli matrices sigma, and valley space. Remember, there's a K and a K prime valley in graphene. And so this is what one gets. It's off diagonal. So this is the kinetic energy term, which is linear because remember it's a conical intersection. It's the Dirac point. And then this is the momentum, which is multiplying the sigma y operator. And what else did I want to point out? Oh, yes, here's the superconducting term, which you see is completely diagonal in anything having to do with the lattice, right? Sigma, the 0 here on the Pauli matrix stands for the identity. So it's the identity, but then off diagonal in Nambu space. So that's what you get. And though I don't think I'm probably not going to show you our analytic results, except maybe some plots of them. We're able to make some progress in terms of treating this low energy Hamiltonian. Now,
Sorry.
Yeah.
Sorry to interrupt.
No
Is
problem.
the spin of the electrons and the holes something you'd be interested in keeping track of?
Right, good point. So I've suppressed that index here, as you notice. And for the purposes of this talk, I'm not going to talk about spin indices. So I'll be talking about lambda levels, which are which are populated by both spin indices. Now, it is very interesting to think about what would happen when you put in spin. But I'm not going to be talking about that at the moment. Okay, we can speculate about it at the end if you like. Thank you for the question.
Yeah. So Harold, I just had a quick minor clarification. First of all, the lattice that you work on, it's a honeycomb then, or?
I was just getting to that.
Okay.
In a minute. Yeah, actually that'll become clearer in the next slide. So
so one more question. What is the term with capital A? Is that the external field or something, or?
Yes, that's the external magnetic field. Because I'm in the quantum Hall regime.
Yeah. And finally, what's that K naught? Why is that K naught over there?
Yes. So the K naught is there because I see maybe my slides are a little bit out of order. I'll point to that. That's because this is for a zigzag edge in which the K and the K prime valleys are separated. So
okay.
K naught is the zero of the valley, and K here is the deviation from the Dirac point.
Okay.
That I'm going to show the Brillouin zone in a minute, and hopefully that'll be a little bit clearer.
Yeah, maybe we should just hold off. Yeah, I'll just hold off. Yeah.
So the idea is, I mean, for the graphene, of course, I want to use a honeycomb lattice, right? But the molybdenum rhenium alloy is certainly not honeycomb, right? So I'm going to use a square lattice for that. And in particular, what I think should happen is at the interface that all of the honeycomb lattice symmetries should be broken. Okay, so I'm not going to be talking about this. There are papers, and you may have heard talks about what happens when you take a honeycomb lattice which has been proximatized, but keeps all of the honeycomb lattice symmetries, and what happens in that kind of a superconductor. That's not what I'm talking about, right? I'm talking about this. So here's my lattice, my honeycomb lattice. Then I'm going to have my superconductor, which is a square lattice, and I've made it. I've made the lattice constant smaller because I want a large density of states, because it's supposed to be somehow be somehow a model of a good high density of states metal. And I've shown you here how we hook things up for both an armchair edge. So this is called an armchair edge because it kind of goes in and out like that. And a zigzag edge. So this is what's called a zigzag edge. It zigzags back and forth like that. And so this is a translationally invariant in the vertical direction. So I have a parallel momentum, which is a good quantum number. The unit cell is, a little larger than one had before because of this hooking up onto the square lattice. And then in the transverse direction, I'm going to have a confined state, right? On the graph, on the honeycomb side, it's going to be confined by the magnetic field, so with a characteristics length of the magnetic length. And on the superconducting side, it's going to be confined by the superconducting gap, and so with the characteristic length of the coherence length. And here's some examples in both of these cases. So the green is the electron. So I'm plotting psi squared on sort of a cut through this lattice. And the green is the electron weight, and the blue is the hole weight, okay? And so you can see indeed that there's there's a decay into the quantum Hall state and a decay into the superconducting state with some rapid oscillations because the Kf of the superconductor is quite high, but the envelope here will be the coherence length. Okay. Now, before I go on, I want to make the point that I'm not trying to do an atomistic sort of simulation of what's going on. This is very much at the sort of model level, and I'm imagining I'm using this honeycomb lattice to produce the this linear band structure, near the Dirac points, but I'm not going to actually be able to do a lattice which has the lattice constant of the actual material in the experiment. Now, before we go on, I just want to point out that this is obviously not a Majorana, right? Because a Majorana has an even mixture of electron and hole, right? And this state does not have an even mixture of electron and hole. It's close, but it's not exactly that. And that's not particularly unexpected because for a system with two spins, you don't expect to get a Majorana actually. So here's where I wanted to show you the dispersion relation now for this mode. So this is a function of K along the interface. And I'm zooming in at quite small energy. So the gap, the superconducting gap is from -1 to 1. And the Dirac point and the cyclotron energy, h bar omega c, are both, substantially larger, 5 times larger than what you're seeing here. Okay, so now we do a little bit of graphene physics here. So on the left-hand side is the lattice in real space, my honeycomb lattice, A and B lattice. On the right-hand side is the corresponding Brillouin zone. This is for the two-dimensional graphene. And now for the zigzag edge, you can see in the real space, I have a zigzag edge going like that. So you want to imagine cutting the Brillouin zone in the vertical direction here, right? And so you'll see that the K and the K prime will not occur at the same point in the Brillouin zone. They're going to be separated, okay? And so indeed, one of them is here, and the other one is there, the K and the K prime point in the Brillouin zone of this system. Right? If you turn and imagine an armchair edge like so, then what you see is that the parallel, the K is going to be horizontal on this scale, and K and K prime are going to occur at the same point in the Brillouin zone, and the Dirac point is going to be at 0. Okay. So this is then the states that we get for a finite strip of this system. And the lines which are hard to see, the ones here, are the edge states on the vacuum side, right? Which we don't care about, right? So these are just the normal edge states between the honeycomb and the vacuum. And you can see that their slope is negative, and that means they're all going in, in one direction, let's say down. The darker lines are the modes that we're interested in. They're modes that are going in the up direction, say, and they're the modes corresponding to these transverse wave functions. And you can see there's 2 of them. That's what I expected, right? I expected an electron and a hole. Remember, I'm solving for both of them. And they've been mixed, right? If they weren't mixed, it would go exactly through 0. Or in the zigzag case, it'd go exactly through the K and the K prime point, which are about here and here. So the fact that they're split and you see 2 distinct curves here indicates that I have this electron-hole mixing. And indeed, I mean, I know I have electron-hole mixing from the transverse wave function. Okay, that slide was a little complicated. I'll just pause. Okay. So how are we going to see that? That's fine, you know, for a theorist, we did that. Oh, there's one other in terms of credits. I sort of forgot this thing down here at the bottom in terms of credits. There's this very nice package called Quant for solving tight binding Hamiltonians in, you know, with funny interfaces and in different geometries and stuff like that, which is what we use for the calculation. Oops, what did I do? There we go. So how are we going to see this? Well, what we're going to do is we're going to inject an electron into this system, right? In the experiment, this interface is going to only be a finite length, but I'll inject an electron and I'll see what comes out at the other side. It'll be, that electron should be a superposition of these two modes that I calculated. And since they're at different values of K, they'll oscillate, and there's a possibility that it'll come out as a, I did an input a hole and output an electron. Anyway, whichever that is. So this is from this paper from the Bainacher group, and then we have our own little way of looking at it. Harsh, did you have something? No? No, okay. Here's my interface, and those are my modes, which I was just showing you. And if I shoot in an electron, this is now the charge, red for electron and blue for hole. The electron comes in, you express it as a superposition of those two modes. You get a beating between those two as you go across, and it comes out possibly as a hole. Okay, let's look at some of the data. Here's the experimental system. So they have a system in which these, this is the graphene. These are some leads that they're using for measurements. This is the superconductor here. And the main measurement that they do is they inject the current and take it out the superconductor like that and measure this resistance, right, between the superconductor and the neighboring contact, like so. Now, there's a couple of possibilities. So if this lead was disconnected and this was in fact the edge state, then you should get zero current between those two because I have an edge state just going from one lead to the next. On the other hand, if this current is really, if this lead is really sinking all of the current, then you see this is kind of a funny measurement to do because it's not along the current path. So it's a non-local measurement, and you would expect it to be zero, also expect it to be zero. Here's the measurement. So I'm going to concentrate, well, forget that. This is the measurement for nu equals 2. And you can see that for nu equals 2 at 3 Tesla, I have this region from about here to here, in which the Hall resistance is very nicely quantized. So I know that I have a nice, well-defined edge state, not going off into the bulk. And yet in that region, right? So if you look at this part of the curve, this is the measurement of this downstream resistance. You can see that it's not zero, right? It fluctuates, and in fact, it can be positive and negative, okay? And here's just on an expanded scale as a function of gate voltage. So I'm changing the density of the system. You see this in nu equals 2. You also see it in the higher Landau levels, nu equals 6, like so. Oh, I was careful to point you towards the middle of the plateau because Here, of course, at the edges, I can see in the Hall resistance, since the Hall resistance isn't quantized, I know that the bulk is participating, right? Once the bulk is participating in the system, then you're not surprised that Rxx isn't 0. So you really want to look at just the region where you know the Hall resistance is quantized so that you know that you have edge states.
So Harold, what are those fluctuations? And do you still have those? I see that when you have those plateau transitions, you have fluctuations in those as well. Do those happen even if you decouple the superconductor in these samples? And
yeah, here it is.
okay.
So this is the case now in which you measure. So it's not quite what you asked, but if I put the current, if I take it out a lead like this and measure just the same resistance, but now without current. So this kind of tests whether it's some property of the superconductor itself. And you can see that in that case, I really get 0. Between the plateaus, of course, I mean, there you get not 0, of course, because there's bulk conduction. But that's the case. And then you asked, what if there's no superconductor? Well, that would be a standard quantum Hall thing. And then again, you would get something like the blue curve, which would be 0. Yeah.
Okay, yeah. But I was actually also wondering about those fluctuations that you see in these data.
Yeah, that's the whole point. Yeah, what are those fluctuations?
Yeah.
So they're going to come from the interference of these chiral Andreev edge states. Yeah. Just a second. So I think I just wanted to show this one thing, which is on a much larger scale, what's happening as a function of magnetic field and gate voltage. And you can see that there's a lot of variation from red to blue, indicating that the sign is changing. And what the experimentalists did is they collected the value of the resistance at all of the minimum and the maxima in some region and plotted it. And what they found is that the magnitude of the minimum and the maximum on average are about the same, right? And then so that's an indication that that these chiral Andreev edge states are on average charge neutral. So how do you get this negative resistance? Well, if I have my electron coming in and it converts to a hole, then when it goes into the downstream lead, it's not bringing in the charge that's expected, right? It's bringing in the opposite charge. So the voltage lead, in order to compensate for that, in order to have 0 current in that lead, has to move in the other direction from the way it would if an electron were coming in. And thus you see what a negative resistance. So just a little bit of math about that. Here's, suppose these are my 2 modes, which are written in terms of electrons and holes. So I can write, of course, I can invert that and write my electron in terms of those 2. And then what I'm saying is, if I inject that state, then on the other side, a distance L away, this is what I'll have, right? And I can write that in terms of the electrons and holes. And so the probability of having a hole is just going to be the square of this, which will have this sine squared delta KL term in it, right? So there's going to be an oscillation in the probability of coming out as a hole as a function of L, or the difference between K1 and K2. Now, L you can't change experimentally, right? That's fixed lithographically. So we're going to be looking for ways to change this difference, the splitting in K between those two things. I think time is starting to run along here, so I'll skip that little comment. Now, so that's fine for probability, but I want to get a resistance, right? Because that's what the experimentalists measure. Well, that's Landauer-Büdeker, right? So I have my system, I have 4 leads. I write the current coming out of those leads in terms of the voltages on those leads. And this is my Landauer-Bodecker matrix in the quantum Hall regime. Now it's a little bit tricky because you have to take into account that that electron can come back as a whole, right? And if it gets reflected as an electron, nothing happens, right? It has the same, it's at the same energy, same voltage that it had before. But if it comes back as a whole, then it contributes, it changes the current contribution by that probability times 2. So putting in those, that Andrei of Reflection into my Landauer-Bodecker matrix, you solve for the Hall conductance and this downstream conductance like so. Now, there's theoretically, what we're going to see in a minute in the results is that I typically get a amplitude which is much, much bigger than the experimental amplitude. The experimental amplitude was about 500 ohms, which is fine in terms of measuring, but the theoretical amplitude that I'll get is, h over e squared, something of order the resistance quantum, because these probabilities are going to vary between 1 and 0. But in the experiment, there's a survival probability. That is, I said that a single particle couldn't go into the system, but that's not quite true. And the reason it's not quite true is this is a type 2 superconductor. And so there's vortices. So there's normal regions sort of sprinkled all throughout here. And the electrons can tunnel into those vortices. And once they tunnel into the vortices, the experimentalists assume that they sort of decohere and disappear into the superconductor. So I don't know how to exactly model all of that. So we just put in a very crude survival probability. And then what you see is in the limit where the survival probability is small, what you find is that this downstream resistance is just proportional to the difference in probability of coming out as an electron or a hole, which is kind of what you expect. Okay, so here's the result, for instance, a typical result, sort of for this geometry then here. And the blue curve here is just the calculation from quant, using the transmission probabilities that come out. I'm plotting here the probability of coming out as a whole. And you can see this oscillation coming from the interference between the two modes. This is as a function of the chemical potential in the normal region. So that's in the graphene. So that's the main thing that the gate voltage does. Now, why does that change anything? That changes things because it changes the value of K at which the value of K parallel for which I get a mode right at energy equal to 0. Okay, that's where maybe I have that plotted somewhere. Just a second. Sorry. Here, this is the K value that I'm plotting, right? And what I'm saying is that as you change mu, you're changing the confinement potential that the electrons and holes see. So this dispersion changes. You change this value of K, so you change delta K, K1 minus K2, and so you get a change in the probability. Let me go back now. Sorry about that. So this is the difference in K that comes out for an infinite interface from the dispersion relation. And if we take that difference in K and put it into the simple calculation that I had on the previous two slides, this is the dashed line is the probability that we get. So you can see the period is exactly right. It does come from the change in K here. And the magnitude we get from the simple argument is, full range from 0 to 1, while what comes out of quant is a little bit reduced. And then in the experiment, it's much smaller because of the survival probability. And then there's various things that we can do. Look at my time here. One important one is you can vary the magnetic field. So again, the same kind of thing is you vary the magnetic field, you vary the confinement potential. So you change the dispersion relation, and so you change the interference effect. And the other one I wanted to point out is, as a function of applied bias, the experimentalists can go beyond linear response and look at the nonlinear response. And that theoretically is just going to probe different energies, right? The linear response is going to involve these two states, but a bias of delta naught over 2 is going to involve these two states. And you can see that delta K of those two states is different from delta K of these two states. So you're going to get some variation like so. And that's seen experimentally. Okay, there's also a story about a vortex, but perhaps I'm running out of time a little bit. This is the experimental observation of the bias. The color plot is perhaps too busy to appreciate, but you can look at one of the traces down here where you can see that they do get a resistance which has some structure in it as a function of applied bias. So what other directions, what are kind of future directions that one could go? Well, this is just one, I focused really on this one experimental quantity, but there are others, and the experimentalists have considered others. And in particular, what about doing really the Josephson case, an SNS case, and measuring then the supercurrent, not the dissipative current that we've done, but really the supercurrent. And so they've done that. So these are the two superconductors. This is the graphene, and they've done it in a way in which they're able to manipulate the number of edge states with a side gate here. They can increase the density on the edge of their sample so that they have more states on the edge of their sample. And they look at then the supercurrent as a function of magnetic field and see, either squid-like or not squid-like, depending on what the system is. Another issue which is just starting to be addressed is disorder. I mean, from a theoretical side. We have some results, and there was also a very recent preprint. Now, you may have noticed that in the experiment, of course, the experimental trace is not beautifully periodic the way my theory is. And my idea was that the disorder would lead to, would give that additional variation. Manesco et al. Argue that the disorder is, more fundamental and actually causing the breaking of the honeycomb symmetries, which allows you to see the interference effect in the first place. So they see a more essential role of disorder in the system. But certainly, I think it would be the combination of the answering Harsh's question before, the fluctuations that you saw there are coming from a combination of the periodic interference effect that you get from our just clean analysis with disorder. And then, of course, there's a question of what about spin? I haven't said anything about spin. And in some sense, spin is the most interesting thing, because it's once you get spin polarized that you can start thinking about perhaps having, trying to make a Majorana or so on. And you can, another very interesting thing to think about is spin orbit effects, because molybdenum rhenium, after all, is pretty heavy and should have, should sort of induce spin orbit effects in the graphene. The graphene by itself probably doesn't have very strong spin orbit effects, but they could be induced in the interface region, which is exactly the region that's important for this kind of physics. So there's some things to think about there as well. And so I've come to the end. I hope I've convinced you that there are these interesting electron-hole hybrid modes at the quantum Hall superconductor interface. And there's these interesting open questions about this system, as well as the possibility of that this is just one example that you can imagine for interfaces of other sorts. And I want to just end with the credits. So Alexei, my student, gets a lot of the credit for this for this work. And of course, we've interacted a lot with the experimental team of Gleb Finkelstein here at Duke. And I would like to thank our funding, so from the Department of Energy, and from for Alexei, he got one of these NDSEG fellowships from the DoD. And with that, I'll stop and ask if there's any more questions. Thank you.
Okay, thanks. I certainly have a lot of questions, but maybe we should allow others to ask.
Sure.
And sorry, Zoom applause is very lukewarm. We really enjoyed the seminar, much more than you realized.
That's okay.
Hey, Harsh, I have a couple of questions.
Go ahead,
Sure.
Sean.
Yeah, this is Xuan Gao speaking. Thanks for the interesting talk. So first of all, I want to ask if those fluctuations which you interpret as the interference effect, can we understand them sort of like a universal conductance fluctuation? I mean, like I know it's different physics, but that since they are not like a periodic, right? And
yes. So yes. So I would say yes and no, depending on at what level you're asking. So certainly there are interference effects which come about because of the interference of these modes, and the disorder is crucial in making them not be periodic. So in that sense, there's certainly some some similarity.
but they are from
more specifically, I think of universal conductance fluctuations coming from the specific correlation between transmission amplitudes, and none of that holds in this system. So more specifically, I don't think it's very strongly connected, but yeah, loosely, it's certainly the same kind of thing.
Yeah, thanks.
So to put it another way, sorry, I'll let you get to your next question, but I just wanted to make sure I understand the answer. But it's reproducible. So in that sense, it's like UCF. But what you're saying is that maybe the statistics, for example, would be different. It's a different system.
Yeah. Yeah. The statistics will certainly be. I would think would be different. Am I still sharing?
No, we just lost the share. Yeah.
Oh, sorry about that. I just meant to turn off the broadcast, not to stop the share, because then if things come up, I can,
Yeah, my second question.
Find the slide.
So my second question was related to the amplitude, the size of those fluctuations. So I was also thinking about like the size should be on order of h over e squared. So can we think, understand that in terms of like the length between the voltage leads being larger than or much larger than the coherence length of superconductor inductor?
Yes. So so there's a number of things that could go into the fact that the magnitude is small. Let me just bring that up. Maybe it's clearest here, where we're showing what the magnitude is as a function of magnetic field. So there's a number of things that could go into that. So one is this business of the electrons going off into the vortices. The other is certainly, phase coherence along the state. Now, one thing you have to keep in mind is that the coherence length, if the coherence length in the superconductor is pretty small because it's this alloy and heavily disordered. But in the graphene, it's pretty big because if I just took, the graphene, the graphene is ballistic and it has a high velocity. And so the coherence length in the graphene is quite large. So I think, but that's certainly a factor that one has to take into account. Yeah.
So I think we should soon transition to private discussion because I know people have to go to class and so on. Maybe Shule, you want to ask a final quick question and then we can go on to more in depth afterwards.
Yeah. Thanks for the nice talk, Karan. So I was wondering the origin of the nonlinearity in the dispersion of the chiral modes. It seems that they're important to the tunability of the effect that the delta K depend on the energy. So,
yeah. Like here, the fact that it's yeah, I'm not exactly sure what I can say about that.
Right, the next slide, that's the calculated dispersion. You have this nonlinearity in there.
Right. Yeah. This calculated, it does have this nonlinearity. These are both calculated. It's just for different parameters.
Yeah.
So, certainly it has to bend over and join the bulk bands here. So there has to be some nonlinearity. You could imagine that it would occur. You see my cursor, right?
Yes. Yes.
Yeah. You could imagine that it occurs, right at the end here, so that this would be mostly linear. I'm not sure why. I don't know what controls that, to be honest. Sometimes we see cases like this one looks pretty linear, right? And all of the nonlinearity is up here. And I don't really understand why that happens sometimes, and other times it's a lot more nonlinear.
Yeah, this is the, okay. All right.
Yeah.
Thanks.
Sure.
All right. Well, I think maybe we'll move into informal discussion. So let's just take a moment to thank Harold to the extent we can on Zoom. As great talk.
You're very welcome. Thank you.
And